So it's clear that astrophysicists have more fun. So let's see if the same is true for particle physicists. So Aran Garcia Bellido is assistant professor of physics here at University of Rochester and member of the CMS experiment at CERN's Large Hadron Collider in Geneva, Switzerland, and the D0 experiment at Fermi National Accelerator Laboratory in Batavia, Illinois. His research is focused on the discovery of new particles and precision studies of the heaviest known elementary particle, the top quark, as well as measurement of the properties of the recently discovered Higgs boson that explains how particles acquire their mass.
Thank you. So yeah, this is the outline of my talk, and I'll try to highlight how we use big data in particle physics with the aptly or very recent discovery of, or Nobel Prize given to this discovery for this particle that gives mass to the other particles. So last week it was announced, and it was given to two theorists, Peter Higgs and François Englert, from a prediction that they actually did with others actually in 1964. And actually this is the Nobel Committee quote, also acknowledging, of course, the discovery of this particle last summer, by Atlas and CMS, and this is my experiment, actually CMS. And so to give you a little bit of an idea of the significance of that discovery, this is a list of the fundamental particles that have been discovered since the 70s to build up this very precise theory that we have now about the fundamental world. And the last one was discovered, basically the last important one was discovered in 1995, and the last boson, this particle that gives force or represents a force, was discovered in 1983. So this is not, these are particles that you cannot discover every year, but rather every 30 years or so. So this is a very, very important discovery. So I'll try to hone in how we use data science to actually help make these discoveries. So this happened at the Large Hadron Collider. This is hosted at CERN. This is an international laboratory straddling the border between Switzerland and Geneva. That's the Geneva airport, and that's the lake in Geneva, and that's up there, that's the Mont Blanc in the Alps. And this is a 27-kilometer or 16-mile long tunnel, 100-meter underground, because you have several populations and cities going around. And I'll mostly concentrate on these two experiments, but there are other four that are also taking data. And so you have two beams, basically, where you accelerate protons, one against in the opposite direction, and then you make them collide in these 4 points where you actually build these huge detectors. And here you have these little beam pipes. They're absolutely at vacuum, and then that's where the protons whiz by. So this is actually a photo of that tunnel 100 meters underground, and these are huge magnets that are used to bend and accelerate these protons, these charged particles, the nuclei that we accelerate. So a little bit of the numbers of this machine. So the energy of each proton will reach 7 tera electron volts in next year. And if that doesn't tell you a lot, that's actually not that much of an energy. That's a total, what a mosquito has flying around. But of course, the deal here is that we've concentrated in a volume that is 10 to the minus 36 smaller than that mosquito. So it's really, really dense. And we do that by accelerating these protons to basically the speed of light. This consumes as much as a little subdivision of a city. So that's 120 megawatts. A nuclear reactor, breeder reactor, produces around a gigawatt. So that's really quite a bit of consumption. We're never producing energy here. Now, all this beam pipe has to be evacuated to very high degree of vacuum, and we all operate all that at almost the absolute temperature, the zero temperature. So it's basically 2 degrees. It's all liquid helium, so that these superconductors are these conductors are superconducting, or these magnets are superconducting, sorry. So what is the beam structure? So how are these protons organized? So we have 2,800 protons running around, again, all in opposite directions. Each of these bunch has a staggering number of several hundred billion protons, and they measure around 7 centimeters and just a little bit of a micron. Okay, so that's a little bit of a fraction of a human hair. And the idea is that we have this, 10 to the 11 in this little segment, and then 9 meters later, another comes, 10 to the 11 protons. Now, they're traveling at the speed of light, so that means that we have collisions happening every 25 nanoseconds. That means 40 million collisions per second. Okay, so this is the huge challenge. And these are the optics that we use to steer these bunches of protons and then make them collide where we want, which is exactly at the center of our detectors. So what are these detectors? These are basically like our CCDs. These are our machines that we use to then collide, to see what comes out of those collisions from those protons. And this is the ATLAS collaboration, and this is the CMS experiment. They're really humongous. They are 4-story. For example, this one is 4 stories high and also like 5 stories long. This one is 8 stories high. They weigh also tremendous, and the important part is that this is all instrumented. So we really have 150 million readout channels that we have to actually read out if we want to keep taking all these collisions 40 million times per second. So that means that actually when the particles of one collision are exiting our detector, we already have had 3 collisions at the center of our detector because these detectors are so large. Okay. So that's quite a big challenge. That's me when it was being constructed. And this is a real data event that we think is actually one of our candidates for this Higgs boson being produced. So here you have one proton coming from this direction, another proton coming from this direction. They have disintegrated, producing this heavy particle, this Higgs in the middle. And this Higgs only doesn't even travel a millimeter. It just decays very promptly into 2 other known Z particles that they in turn decay to 2 electrons, these are the green lines there, and 2 muons, which are heavy brothers of the electrons, which are these red particles. Now these other little tracks and other little particles that come out are the debris of these protons interacting as well. Okay, so these 4 elements that come out are the ones we're looking for, but we also have to deal with these other tracks and these other particles that are produced when we collide so many protons together. So that's basically our event. That's what we call a collision. And by reconstructing these muons and electrons, we can say, here was produced a Higgs boson and not some other process that we already know about. So this is a little bit of a representation of this problem. So here you have the rate at which we make these collisions versus the size of each one of those events. And these are the other 2 experiments at the LHC, and we're sitting here with both large size of the event size, and then also they are coming at a very high rate. Other experiment takes smaller size events, but at much faster rate. And this other experiment, when they're colliding lead atoms, actually instead of protons, they collect very few events, but very, very large in size. So the idea is that if we just took data at that rate, we would collect a petabyte per second. And only to store that, we would have to spend $1 trillion, okay, just in storage. Of course, we cannot do that, and we don't need to do that anyway, because most of the collisions that happen are already known physics. Those are things that we're not really interested in because we've already measured very precisely. And so the idea is that we need to trigger on the type of events that we want, for example, as you've seen before, so things that have, for example, 1 or 2 electrons at very high energy, like in this Higgs case. And this is what the trigger system does, and basically reduces the volume from 500 events per second to, at the end, to 500 events per second, and each one with a size of around a megabyte. So we have a factor of reduction already of 10 to the minus 5, and these are events that we're just really throwing away. Of course, you have to be smart about it and not throw away events that you would later regret that you threw away because they contain new physics that you've never seen. So this means that in the end, we're only going to be recording a few petabytes per year. And so to put that in context, this is the LHC annual output of all the experiments. So that's around 15 petabytes. That's the business emails, again, in 1 year. And this is the Google search index of around 100 petabytes. Now, you'll see in a minute that we're actually going to grow that size to around 2 times that, which is basically, that's the content uploaded to Facebook, again, every year. That little dot there, if you're curious, that's the tweets in 2012. So anyway, this is just to see, and we're going to grow that actually. This is just the raw data, and you'll see in a minute that we're actually going to make it much bigger. So how this data acquisition problem or system works, this is basically where we really need to come in and then be very smart. This is the way we need to have this rejection factor of 10 to the 5. So we start off with 40 megahertz or 1 petabyte per second, and this is all custom hardware that the several hundred universities and several thousand physicists have actually worked hard to do and maintain and work. And so this basically looks at several parts of your detector and says, okay, you have an electron here with enough energy, let's see that event in more detail, and then you miss the next collision. But if that electron is not interesting, then you throw it away, and then you're ready for the next collision 25 nanoseconds later. So if you want to keep that event, then you send it to this huge array of a farm of PCs. We have around 1,500 machines. This is for one experiment. And one of these nodes has around 40 milliseconds to actually make a decision, read out the whole 4-story building, 150 million channels, and then send it off to the rest of the computing grid to further analyze and actually study that event. So at the end, we end up with a rate, which is still huge, of 300 megabytes per second. And we're running 9 months of the year, every 24 hours. So what's the next step? Okay, now you have these events saved, then you want to analyze them. And this is basically the crux of how CERN has operated and how all these big experiments now function. So CERN does the first pass at reconstructing that initial event. And then it distributes it to a series of 11 centers around the world. We have 2 in the US, one in Fermilab in Chicago and another one in Brookhaven in upstate New York. Oh, sorry, in Long Island. And then several others around in India, Europe, etc. And these are in charge of doing actually the permanent storage and further reprocessing, and then doing also a little bit of user analysis. And finally, you have the tier 2, which are basically large universities and centers that also provide computers and storage facilities, and that's where the bulk of your simulation and end user analysis happens. All in all, you're doing 2 million jobs per day, okay, in this whole system. And here you have the absolutely staggering numbers. This I just pulled off on Monday out of the web. We have 354 petabytes available for storage. Okay, this is in mixture of tapes and spinning disk and just hard drives. And then we have almost 500,000 logical CPU cores available for all those jobs. Again, here you see the different layers. And it's not only Atlas and CMS, this LHC computer, the LHC experiments, it's also the other experiments at LHC that benefit and use this. So this is a snapshot of the tier 1 at CERN and how the ramp up of simulation of events and user analysis just before the July 12, 2012 announcement. And this is a similar number. So this is basically the number of running jobs, okay, per day. And this is the number of reprocessed or re-reconstructed events in the other experiment in CMS. And you saw that we have a huge peak in January just to be ready for things to come out in July that same year. So how did we get, if I just told you that each experiment outputs around 3 petabytes per year, how do we get from that to 350 that we need actually on the grid? And the reason is that we actually duplicate the raw data just in case something happens. We also need to produce, and this is a large part of that, huge amounts of simulated data. So we basically need to say, if we know a known physics process, we need to simulate how that actually has occurred in our detector, in each of our detectors. And so we have both the signal events that we want to model and the background events. Okay, so things that we know how the Higgs is going to be produced and decay, and we know how other 2C bosons can be produced and then decay. And they're different, and we know the laws that govern each of those processes, so we can simulate billions and billions of those events. Okay. We then, each analyzer won't look at all these billions of events that we've recorded, and we'll just look at a subset of those, and we'll want to select certain variables and certain types of events, and so each one of us will then produce several reduced data sets that we will also use and also store in this database in the grid. The idea of this grid is that you basically don't have to know where your data sits. I'm just interested in, for example, events that have 2 electrons and 2 muons. I just send my job to the grid. That data may be sitting in India, not in New York, for example, and the job just routes itself to India, fetches that data and runs on a computer over there, and then sends me back the results to my computer in my laptop. So that's basically how it works. It's all this big distributed computing. So you have these several then copies of your analysis that every analyzer does, and then you also have these several copies around the world. And this gives you a snapshot of all the traffic of sending back and forth jobs and data all throughout the world. So again, let me go back to see what happens with this data. So this is a recorded real event. So that's like a picture of a real collision. You send this, and then you have to reconstruct it. So basically, if you say that you have hits in your detector where a track went, then you need to make that a whole track, and there's a pattern recognition problem, and then call that an electron if it has the properties of an electron, or just call it a pion if it's a pion, or a muon if it's a muon, okay? And then you need to say if it's positive or negative, and then just basically call it a particle instead of just the hits in your detector, okay? The raw data measures around 1.5 megabytes per event, and then here's where you select, okay, I only want events with electrons or muons, for example. That gets reduced to around 0.25 megabytes per event. And then you finally have an event summary, which can be very small, in which you don't need to know all that hits, but just the track, right? Just the direction, the function that describes that particle. Now, here comes the interesting part. You also have to do, again, this simulation. So you need to know how your signal would look like if you were to produce it in your event, in your detector, and also all the other known backgrounds that we already know about. And you have to do the same game. You have to then have a simulation of your detector with what is the, a typical electron of this energy will leave a measure of a number of hits in my detector that look like this, and then basically compare it with the data, and then run it through the exact same chain that you run the data over. Finally, then you get your reduced data, and that's what you and your student can analyze in your laptop, basically. And then you identify those particles, select the ones you want, and then you can do a statistical analysis, and then you send your paper for publication. So that's basically how it works. This is how a typical event, or 19 events, look for us in this reduced format, okay? So this is, for example, you have the lepton energy, the lepton, one lepton angle, a jet, that's a pion, for example, that decay with some energy and some angle, and this is for the first event. You can have some event-wide weights for those type of events, for example, this is in the simulation, and you have huge rows, so each row is one event, one collision, in this case of some simulated data, and each column is one of the variables that I'm interested in. And here you can go to 200 variables. So that's basically how the data looks like. And we use this root format that was developed with a team basically of 5 people over 10 years, and this basically everyone in the world is using this for higher energy physics. So then you have this analysis, these events that you've already reconstructed. You want to now find the signal in your billions and billions of recorded events, and this is to give you an idea. So if you produce around 10 to the 8 events, in your collisions, those are the known physics ones. This is the ones that we're not interested in. But for every 10 to the 8 that you produce, you basically, for the Higgs, you only have around 10 to the minus 1 that you produce. So you only produce 0.1. So you would need to double that or multiply that by 10 to produce one Higgs event. So the trigger has already brought us down to a level of 10 to the 5 rejection. This data mining now has to bring you from a level of several million also, right? So you need to find that one in several million events that you're looking for. So this is basically where we now really rely very heavily on machine learning techniques like neural networks, decision trees, and support vector machines. And a few years back, this technology was a little bit frowned upon by the community, and it would have been very difficult to make a claim of you've discovered a new particle relying only on these techniques. But I think people have now used it enough and show that they work reliably to actually be very confident, and we've been using them for the last 5 years for everything, basically. These also then require a large number of simulated events, so you train them and you know these multivariate space, how to put the background in one side and then the signals in the other side. Okay, and then we can also use brute force probability. So we assign a likelihood that one physics process has produced this type of event, and another physics process has produced this type of event with one lepton only, and here with 2 leptons, for example. And you know the laws for all these processes, so you can then simulate it and play nature here. Okay, so this is the example of this data mining. For this Higgs to 2 jets analysis that formed part of this discovery last year, we started from the 11.8 billion recorded events. This is everything, all the events that we wanted to look at, okay? And then we brought it down to around 6,000 events that only contain this type of final state, the 2 objects after your collision, and the satisfies certain cleanliness and properties of these photons. They have to be very clean, not have any other electrons around, things like this. Out of that, we expect only 170 collisions to actually come from the Higgs particle. And for this, you actually have to generate over 100 million events just to get that number. And here you see the different background compositions. So these colored histograms here represent the known physics processes and how they add up to the dots here. So the vertical axis here is events that we've collected, and how they add up, and how we can actually describe this very well. Okay? And this is the signal that you would expect from this Higgs, this little tiny bump here at the mass of 125 or so. And this is actually the discovery plot, where you see that this is the errors, these yellow and green bands are the errors that we expect on the sum of these backgrounds that we've simulated. And then we see the data have that bump exactly at 126, which is where the mass then of the particle was produced. So this particle was produced 126 and then produced 2 photons back to back, and that's what they reconstruct back to an energy of 126 mass, basically. And so that's one of the channels that we use for the discovery. The other channel is where you produce the Higgs, and it decays to these 4 leptons, the event display that I showed. In this case, we also use heavily these probabilistic or these multivariate techniques, where here you have the signal and how it peaks close to 1, and here you have the sum of all the backgrounds, or one background in particular, that kind of peaks towards 0. And so this is also what we use in this multivariate analysis to then say, okay, this event has a probability of 0.9 of being signal, or much less for being background, for example. And that's again the bump where you see that you've reconstructed the 4 leptons, and they give you this signature for the presence of this new particle. You then have to do the statistical significance, all right? So we've seen that huge bump, just by eye, you could say, well, this is clearly something there. If you didn't have this red histogram, there would be something missing. The data wouldn't really fit your expectation, but you actually want to measure that. And in particle physics, we've come to this completely arbitrary standard, if you want, that we require that the p-value, or the probability for a background only hypothesis to shift up and give you a signal like the one you observe in your data, to be 3 times 10 to the minus 7, that's 5 standard deviations in a Gaussian, or the probability of 1 over 3.5 million. Okay? Again, these are stochastic recordings that we do. So you're basically saying, okay, what's the probability that if I toss a coin 50 times, all 50 times I'm going to get heads? That's not going to happen very often, but it might happen. Okay? And we have to assign these error bars to that probability. And so what you do here is you can generate then 3.5 million repeats of the CMS experiment, right? So we make up data in what we call these toy experiments or pseudo experiments, picking and choosing from these billions of events that we've chosen from the Monte Carlo, according to the correlations in our errors and how big a sample we actually select out of those 6,000 events that I told you about in that channel, for example. And then we recreate, we play nature, if you want, and say, okay, if we were to run CMS, my experiment, 3.5 million times, would there be one result in the data that would produce this bump in this distribution? And if the answer is no, then you have that level of certitude. Okay, and so that's it's very strict, and this comes from years of seeing 2 sigma, 3 sigma particle or evidence for particles appear, and then the next experiment look in the same place and don't see anything. Okay, so 5 sigma we deem is the threshold to say, okay, we're sure now this is very, very difficult to replicate if this is not a real signal. Okay, and for this we also use this very specific specialized code that we've actually developed, also with help from statisticians. Okay, so let me then bring it down to the US. In the US, we have this open science grid, which is funded by DOE and NSF, and it's just been extended until 2018. And this was mostly driven by the momentum from the LHC Tier 1 centers here in the US. And it basically is a consortium of small, of around 100 universities and big labs, where you pull together all your blue gene type of clusters, and then also the Tier 1 and LHC machines. And then you can actually share the jobs and the CPU cycles that you have in there. This has delivered up to 2 million CPU hours per day. And currently the use has been around 60% for the LHC experiments, 20% for other high energy physics experiments, and then 20% to others, which go from cognitive science, earth sciences here, chemistry, biology, computer science as well, and many other projects. Actually, out of the 500 publications that have been produced from using this grid, more than 110 have actually been from these other than HEP fields. And here you see the hours spent on these jobs, and you see this huge increase as the more resources have been available. And here you see how the US participation here was critical for the July announcement of the Higgs in running many jobs. This is Atlas and this is CMS, and these others are the other fields that also contribute. So really, this is a framework that we share between many, many universities, so you can send your jobs there and then do it. Let me then very quickly go to the future needs. We just went through this decadal survey of what we're going to need in the next 10 years. And this actually ties up very nicely with what Eric just showed you. Look at this. This is the LHC now. This is in 5 years. So it's a factor 2 or 3. And that's a factor 5 from where we are now by the time we reach 2020. So this is the size in raw gigabytes per second that this upgrade of the LHC will provide in the next 10 years. And you here have many other physics and astronomy and astroparticle physics experiments. This is dark energy survey. And look at this. This is the square kilometer array that Eric just described. This is going to blow us all out of the water. Okay, so this is really going to be incredible. So this is also a sign that astroparticle physics is also catching up with high energy or particle physics per se. So let me then conclude. So particle physics, by its own nature, has been really a driving force since the very beginning of what we call big data or data science, and we've benefited greatly from advances in the technology, and we've set up this distributed computing that really took a long time to prepare for and actually be ready, but now it has delivered fantastic results. All the results that all the publications that you see coming out of the LHC have basically used this technology and wouldn't have happened without it. Now the rates as I've just shown will continue to grow, and also with these other branches of physics if you want. And we will reach exabytes by 2018, and this is going to put a huge strain. Now in particle physics, because also we have such a large community, we have a little bit of an inertia here. And for example, we're still not exploring in detail this multi-core technology, parallelizing jobs, and the GPUs, but we probably will need to, and we're beginning to study those avenues because we really need to keep up. And also, you've seen that we have a huge problem of storage and keeping this data for years to come. And perhaps we're also studying things with industry to move to virtual data or cloud computing even. So you've seen that this morning that industry has really caught up, and many other, like biology and biophysics, has caught up with high energy physics, and in many cases surpassed it. But we're still planning a lot of technological advances that will happen in the next 5 years, and we're still continuing to collaborate with Intel, Oracle, Google to keep up with them and benefit both them and us. So we're still driving this high area of technology, especially the high throughput and distributed computing. And we've really made, because of our nature of collaborating in between institutes and between countries, that we're really well set up to be a big participant in this big data project. Thank you. Questions? Yes?
So if you have 150 different sites at which these petabytes of data are stored, does latency ever become an issue? Or?
Yeah. So you have to have a certain. I don't know if it's working. You have to have a central brain that basically decides when a site is becoming overloaded. Yeah. And so, but but then you can switch to other. The problem is, the data may be sitting in India, but then if that site is unusable, then you have to go to somewhere else, right? And we still see failures of that happen, right? So this has been blood and tears throughout many years when you still need to babysit all these jobs, and but now things are really running very, very smoothly after all this experience.
Is there any time at which you need a certain data set within nanoseconds, or?
Not really. Not for the final analysis. Yeah. So all that happens at the tier 0 at CERN, and it's local, and then it can happen very quickly.
Okay, thank you.